Yeah. Yes. So another concept what we were seeing was the epigraph. So all the region above this graph, right? So this is the epigraph. So this is the epigraph. So if this function is f, we will denote this as epi of f. This is epigraph of f. Okay. So the important thing is these two alpha sublevel set and epigraph, these are set. Okay. So this is the set containing all this point, and epigraph is a set containing all this point. So these two are sets actually. Okay. Let's continue. Now we were at Jensen's inequality. So we saw that from the basic definition of convexity, we can extend that definition, right? So this is the basic definition of convexity. So now by observing these values of theta I, like then we can say that, okay, this is like probability distribution values, which adds up to 1 and take values between 0 and 1. It's like probability, right? So then we replace, we made a general statement where these thetas are replaced by a probability distribution value. Now we can write this as this guy as expectation of x, and which is less than or equal to expectation of expectation of the function values. Yeah, so this was Jensen inequality. So you don't need to remember this. If you have any doubt, just take a convex function and just see what it is. Just this is like expectation, right? You are this is like a weighted average in theta and 1 minus theta. So that you can replace like expectation of x, and this is the weighted average of the function values. So that is expectation of f of x. Yeah, so that is one thing. Yeah, so this is for remember, this is this Jensen's inequality. Here what we are saying is for convex function. If you take a concave function, then you have to flip the direction of inequality. Yeah, so that's it. Yeah, one more thing, one useful interpretation of Jensen's inequality. Let's say I have a function, convex function f of x. Let's consider it as a power or something in some scenario. I'm just making a toy example. So we have a power function which is like this, and we have a variable here y. So I should make it x, right? Yeah. So this is x. Yeah. Now what I'm interested, what I'm looking is like to the, so this is x0. And this point is x0. Okay. I think, yeah, this is actually f of y. The function is f of y, and at this point it takes value f of x. Okay, so what I'm saying is what happens when I add a random variable to x. So we have a point x, argument x. At that point, the value of the function is f of x. Okay, this is the value of function at a particular point x. Now I am adding a random variable z to this argument. Then I'm observing what will happen to the function value on an average, because here we are talking about random numbers, right? So on expectation, the expected value of the function, how that is changing. So here, important thing is I am adding a zero mean random variable. For example, here I am adding a normal random variable with zero mean and variance 1. In that case, what happens? Just we will plug that in the Jensen's inequality. So x we will replace with x plus z. Okay, z is the random variable. So you are taking expectation of this. So expectation of x is a constant. So expectation of x will be x itself. Expectation of z will be 0 because we consider 0 mean random variable. And now this is like expectation of f of x plus z that we are interested to see what happens to that. So this will be just f of x, which is less than or equal to expectation of f of x plus s. So what we saw that we had a function value, we have a value, we have an argument x and corresponding function value f of x, and I added a random variable with a normal distribution and having zero mean. In that case, this cannot decrease the value of a convex function, right? So whenever you add a random variable with a zero mean, then my expected value of the resulting function would be greater than that. Okay, so randomization, or more specifically, adding a zero mean random variable to the argument. So this is what I mean by randomization. So if I do that, then the function value is expected to be greater than the value of x. This is happening because this is a convex function. If it's not convex, this will not happen. So it's just an intuition interpretation in a specific case. Yeah. Now let's move to the next topic: operations that preserve convexity. So far we saw one or two, a few techniques to check convexity. One was we saw first order and second order condition, and we also saw the basic definition using the Jensen's inequality, right? Now the thing is, this is not, this will not work always. These methods, sometimes it's very difficult to find Hessian metrics because we have a complicated expression, we cannot differentiate. Maybe even if you can differentiate, it is very difficult. Or when you differentiate, you will get a very big matrix whose is very difficult to determine, to find the eigenvalues to see whether it is positive definite or not. Or sometimes you cannot apply the basic Jensen's inequality, which will be very difficult. So in that case, there are many scenarios where we can decompose the original function, which may be big and complicated, into small function, and we say that okay, these small functions are convex, and we are making the big function our original function using the small functions and using some specific operation which preserve convexity. So by just seeing the function, we can visualize that okay, this is coming from this part, and combining using convexity preserving operation. So my original function or the big function is convex. So this is the most useful tool that we use most often in optimization. So we should be familiarized with the functions that operations that preserve convexity. So let's see what are they. So first one is yeah, this is a simple one: positive weighted sum and composition with affine function. So first is non-negative multiple. Okay, you have a function f, you are just multiplying with a non-negative quantity. So you have f of x. Now you are saying that okay, 2 f of x, if f is convex, then 2f is convex, or 5f is convex. Yeah, so of course f has to be positive. If it's negative, that will flip the function, right? Then that will be a concave function. Yeah. Okay. Yeah. Now the sum. So you have two functions. Then if you take the sum, that will be convex. And composition with the affine function. So these are simple examples. So we don't, you can just prove this using the basic inequality very easily. We will not go through that, but it's very simple. Composition with affine function. So you have a function f, which is convex. Now what I'm saying that I consider f of ax plus b. Okay, so you have x, then you are taking an affine function of that, and then you're passing that to the argument of a convex function. Then the overall function will be convex. in X. Okay, some example. So yeah, so some example. Yeah, first one is log barrier for linear inequalities. So this is the log barrier function. Okay, let's not much worried about the name. So just see the function. So the moment you see the function, so it's not a simple function. It looks complicated, but now we are ready to go, right? How? Because we know that minus this is an affine function. Okay, so we have X here. Okay, you are taking an affine combination of F here and then passing that to a convex function. Minus log is concave, minus log is convex. Okay, so X affine function, log, and then adding it. So addition also preserve convexity. So the resulting function is convex. Okay, yeah, one thing is here we are talking, this is the way I wrote is slightly confusing. I don't have this guy to be convex. I mean, I will explain, sorry. Because this may confuse you. I'm just talking, my pencil is slow. So, no, what I'm saying is, no, all affine functions are convex. They are both convex and concave. So I will clarify what my point is. So here what I'm talking is, I have a convex function and the argument is an affine function. Okay, so I cannot generalize this for any convex function. Okay, what I'm saying is, if I put any convex function here, it need not be convex. Okay, that we will see very soon. So here I'm just talking about a convex function and its argument as an affine function. Okay, so converse function of an affine function. That's what I'm saying. So so this is just for affine function. We cannot replace this with any converse function. That will not work, but it will work for some cases that we will see. Yeah, so that is one case. Another case is norm of affine function. Okay, yeah, so we saw that the norm is a convex function. Now instead of here, the f is our norm. Okay, so we have norm of an affine function, so that will be convex. So this is very useful. Every norm, right? No, norm between 0 less than 1. Every norm we can say, but what we saw is that norm with, if p is between 0 and 1, it is not a norm, it's a quasi norm. So when we say norm, p less than 1 is excluded. Okay, so this guy is very important because often in your research you will come across something like this, x minus c square, something like that. Okay, so then the moment you see that, you should realize that, okay, this is an affine function inside a norm, which is a convex function. So affine function inside a convex function is convex. Okay, so that's the thing. Now next guy is point-wise maximum. So what is this? I have a function f. Okay, how I am defining the function at any value of x, for example x0, how the function is defined. It is like that. It is maximum of so I have m different function f1 to f. Okay, so I evaluate the values of this function at the same point x, and I will take the maximum. So this is point-wise maximum. At each point x, I will do this. Okay, so this is point-wise maximum. So so then the domain of f has to be the intersection of all the domain of this. So let's see an example. Don't worry. So here I have a function. So I'm considering two functions here. F of x is point-wise maximum of f1x and f2x. So my f1x is this, f2x is this. Okay. Now what I do is I take the point-wise maximum. Of course, I am my domain. So this is very important. My domain should be the intersection of the two guys, domain of two guys. So what is the intersection here? So we have the first one, let's say the first one has domain like this, second one has domain like this. Yeah. So the intersection will be this guy, right? So the resulting domain will be this. Okay. And so what is the value here? So I take the pointwise maximum. So I have this resulting function, right? Go, right? So take each point here in this domain and consider the maximum value. So that then you will get this. So this is the maximum of this two function, and which is a convex function. And here, yeah, so other thing is here we can think about this in terms of epigraph also. So epigraph of maximum function, epigraph of this maximum of different function f1 f2 to maybe f1 will be the intersection of the individual epigraph. So how, so that is clear from here, right? So like for example, here you have epigraph like this, right? Here you have epigraph like this, right? And then finally the maximum function has epigraph like this. So that is the intersection of these two epigraphs. So remember, epigraph is a set. Now we can define the intersection. Yeah. Yeah, so that's what the pointwise maximum. So some examples: piecewise linear function. So if we have a piecewise linear function of this form, max of different affine functions, then they are convex. Let's see one example. So I am defining a piecewise linear function of x here, which is max of x and minus x. So you have x here. This is the graph of x, right? And this is minus x, okay? So when you take max, what happens? You will get this guy, right? So that is basically our absolute value function. Okay. Yeah. So then that is convex. So if someone asks you why absolute value function is convex, you can answer in this way. Okay, this is the maximum of x and minus x. So piecewise, pointwise maximum preserve convexity. So the absolute value function preserve convexity. Yeah. Yes. So yeah, that's one thing. But one important point is we are considering the piecewise function just in this form. We cannot say that all piecewise linear functions are convex, because here we have a function which is piecewise linear, right? This piece is linear, this portion is linear, right? So but this is not convex. So this statement is not applicable to all piecewise linear function. It's just for the functions of this form. Yeah, next function is sum of r largest components of x. So we have a vector x, x1 x2 up to xn, and so I have a very complicated function or crazy function, which is you pick r largest component and sum of this. So if I am fixing the value of r to be 3, and the first 3 are the largest guys, so I will just sum these 3 guys. Okay, so that's this function is doing. So how can we deal with this function? Because
I went out.
Yes.
Suppose we have like n numbers. We are saying like we have to add r numbers, largest numbers from that. Then how will like understand up to what we have to consider the largest number?
You have, for example, 50 numbers.
Yes.
You are saying that take the large 3 number of the
Okay.
vector.
So like 3 and 4 like that we have to specify that.
Yeah, that's why some of the are larger.
Okay.
So you have a vector with 50 components,
Mhm.
and you are like if R is 3, so examine all the 50
All the
components
and
and pick up the largest 3 and add them. That is this function. Okay, so how can we say that whether this function is convex or not? So yeah, so here is the trick. So we can write this in terms of uh, a maximum function. Okay, so what I do is, so let's this be the vector x1 to xn. So let's take one particular vector a1, okay, which is a1 transpose, which is having this form. So 1 1 0 1, everything else is 0. So I am explaining with a simple case where r equal to 3. So I put 3 ones here. Okay, all others are 0. So what happens when you multiply this together? It will be x1 plus x2 plus x4. Okay, now what I do is I vary the position of these 3 ones. Okay, and I form all the possible combinations. Like first I will put 1 1 1 0, then maybe 0 0 1 1 1 0, like that. So I examine. So in fact, what I'm doing is I am examining all the possible, what to say. I am picking all the possible combination, all the 3 uh, combinations, okay, and taking the sum and examining that. Okay, so choose. How do you choose that? How many choice we can make? You have n vector. From that you are taking r, right? So if it is 50 and 3, like, so we have to make 50, choose 3 choices, right? So then you have, like here, like you have an affine function, right, or a linear function here. Like that you have 50 C3 functions, and then you take the maximum of that. Okay. Yeah. So the point is, this function was not simple function. Yeah, sum of largest. This is not easy to visualize, or this is we cannot use any method like a Hessian or something. It's very difficult, or you cannot use a normal Jensen's inequality for this. This is very difficult. But if you know the trick, like you know the fact that point-wise maximum pressure of convexity, so you can easily use that fact, and just within second you can say that this function is convex. Okay. Yeah. Yeah. So we will also see a small proof for how the point-wise maximum preserved convexity. So let's consider f of x to be maximum of two function f1 to f2, but this can be extended to any number of functions. Okay, let's consider two functions here. And now what I do is I examine this quantity because I have to see whether this is convex or not. So I take the left side of the inequality, Jensen's inequality. So theta, of course, theta should be 0 to 1 because we are taking convex combination. So what is this? This guy, it is maximum of f1 of this argument and f2 of the same argument, right? And now what I do is I know that f1 and f2 are convex. That was our assumption, right? You are taking maximum of convex function. So f1 and f2 are convex. So just apply the inequality here. So you are taking maximum, but now you are increasing the argument, right? Then of course that maximum will also increase. Okay, right? So then I can say this, right? Uh, so I have now this expression by applying the inequality, basic inequality. Now what I do is, so here if you see maximum of two guys, first one and second one. So like I will take a simple example. So we have maximum of a plus b and c plus d. I can say that this is always greater than, I will pick maximum of these two, a and c, and add that with maximum of b and d. Okay, this will always be greater than this. You can just check with some simple examples, you will see this. Okay, but that makes sense, right? Instead of taking the maximum of these two sum, that you are just taking the first guy and picking the maximum of that and adding that with the maximum of second guy. So that's what I'm doing here. So I pick these two guys here and take the maximum of that, and the next two guys here take the maximum of that. And now
But then the inequality sign will be like,
sorry,
because inequality sign will be like opposite, right? Because first function is 7 and second is 8. 7 can be greater than 8, right?
mm, I think I made a mistake here. Yeah, I made a mistake here. Sorry. This is opposite, right? So when you take maximum of, pick the maximum from these two and add that, that will be greater. Okay. Yeah, correct. Yeah. So then we can, it's a inequality with the same side, right? Same orientation. I do this now. Theta is a positive quantity. I take that outside. It will not affect the max. I take it out. Now I have max of f1 and f2. Here also max of f1 and f2. Okay, just that, that is our original function f of x. This is f of phi, right? So now we prove the inequality. So this is how we prove maximum preserves, point-wise maximum preserves convexity. Yeah, so we saw that. Now next is point-wise supremum. Sorry. Yeah, point-wise supremum. So we saw what is maximum, point-wise maximum. Now we are seeing what is point-wise supremum, how that is affecting convexity. So here, are you familiarized with supremum or infimum? So that's a basic concept. So supremum is something like a maximum, but it is similar to maximum, but it's not the same. It's different in some aspect. So let's see what is supremum. So supremum of a set. So we have a set, it has a supremum, okay? And that supremum of a set is the smallest upper bound of the set, okay? So I will explain. What is an upper bound? Upper bound of a set S is defined as B. We will say that B is an upper bound if you pick any element from the set, that should be less than this guy, okay? So that's like intuitively it's like when you say upper bound, right? Upper bound of a set, like if you pick any element from that set, that will be less than this upper bound, right? That's the bound, right? Like if you consider lower bound, then any element will be greater than lower bound, right? So here is an example. So my set is this in a real number. Yeah, so I have said this. So what are the upper bounds? So all these green regions are upper bound. So I can say that this point is an upper bound, because if I take any element from this set that is less than this point, right? So that's an upper bound. This is an upper bound. This is an upper bound. Okay. Then now what is supremum? It is the smallest upper bound. So that will be this guy here. Okay. So we have many upper bound. From that we are picking the small sky, that is supremum. Similarly, we have a concept infimum. So it's just a reverse. So you go for lower bounds. So these are the lower bounds, right? Because if you pick any point here, that will be greater than this, right? You now you pick the largest lower bound. So that will be this guy. So these are the concept of infimum and supremum. Now, how supremum is different from maximum? It may look similar to maximum, right? So you have S here. So this guy seems to be maximum, but there is a slight difference in some cases. For example, when you let's first take this example. So the set is real numbers between from 1 to 5, okay, including, so this bracket means including 1 and 5. So what is the maximum of this set? It is 5, right? What is the supremum? That is also 5, okay. Now, here is the difference. Now I consider a different set where the five is not included. Okay, so this is the set is not crossed on this side, right side. In that case, what is the supremo? Again, I can say that 5. If you pick 5, 5 is an upper bound. That is all the guys here is less than 5. But what is the maximum of this set? 4.9.
Yeah, 4.9.
That's not one thing. Then the moment you say 4.9, I will say 4.91.
Yeah, then it's
Okay.
like
The moment you say 4.99, I will say I will add 0.01 to that. Okay. So you cannot find maximum here. Maximum does not exist here. So that's the difference between supremum and maximum. Okay.
in open set we can't find.
Yeah. So we this is a widely used concept, but it is something similar to maximum. If you have difficulty in visualizing what is supremum, you can just replace that with maximum just for the sake of understanding. Okay, just take this as maximum, but remember that both are not same. That is difference. Yeah, so now we see that so like maximum, pointwise maximum preserves convexity, supremum also preserves convexity. So some example. Yes, some example. One is supporting function. So what is a supporting function? Is that so you have a set C, okay, and supporting function, yeah, is defined as supporting function of set C evaluated at argument X is defined like this. You pick all y's from the set C, okay, and then take the inner product with this X, okay. So you have different so y1x, y2x, like that. You have different inner products from this set and take the supremum of that or maximum of that. That is what supporting function is doing. So yeah, so we don't go into detail where this is applied or not. Just understand that, like this is just an example. So like this is how supporting function is defined. Now the question is whether supporting function is convex or not. Now we can say that, okay, this is a pointwise supremum and hence this is convex. And now other thing is distance to farthest point in a set C. Okay, what is that? So you have a set C here, okay, and my f of x function evaluated at x. How do you define that? You form all the possible distance, pick y1 and find what is this distance, which is x minus y1 Euclidean norm of that, right? And pick y2, find the distance, okay, and like that you find all the distance and take the maximum of that. Okay, so y, pick y from C and find all the distance from x and consider the maximum of that. That is the distance to maximum function. So remember here, I just set the concept for using the distance, Euclidean distance, because we are very familiarized with that one, but this is applicable for any norm. Okay. So sometimes if you like pick some norm, we cannot visualize what it is doing, right? So that's why I explain using a two norm, but it's applicable to all norm. But another important point here is, here we do not put any constraint on the set A. We didn't say that A is convex or not. Here, the set C is this set convex? No, right? You can pick any 2 points here, draw a line that's lying, some part is lying outside the set. So this is not convex set. So for this property to be satisfied, the set C need not be convex. Okay, that is an important thing. So we can write it here. A need not be convex. It can be any set. There is no restriction. Yeah. So another guy is maximum eigenvalue. So this is a very crazy function. Maximum eigenvalue of a symmetric matrix. So we have a symmetric matrix X. Okay. Now my function is f of x is given us. Function f of x is given us. You take all the eigenvalues of x and then pick the maximum guy. That's the function. So this is not an easy function, right? So just this is not an easy function. You are given like a 100 cross 100 matrix, and then you find all the eigenvalues and find the maximum eigenvalue. You cannot write it on a paper or maybe in MATLAB also. It is very difficult when the value size of the matrix increases. So then how do we solve that? Whether this function is convex or not? Now we have an equivalent definition for maximum value of maximum eigenvalue, which is given by this. Okay. So what is this saying? You pick y such that the norm of y is 1, equal to 1. Okay. And then you observe this quantity y transpose xy. Okay. And take the supremum of that will be the maximum. So we don't go to the proof of this. You can search for the proof. Maybe in Boyd's textbook, I think in appendix they have a proof, or like you can search in other textbook. But this is a well-known expression for maximum eigenvalue. So to find this function, whether this is convex or not, what we do is we seek the help of this expression. Now we can say that, okay, what is this function? Supremum of, is this convex function? Positive semi-definite. We didn't say it is positive semi-definite, right?
It seems to be like if it's the value greater than or equal to 0.
No, what is so what is the argument of this function f of x?
So it's saying like
Remember, is it a quadratic function or linear function? That's my question.
okay.
So basically, if you have confusion, just see what is the argument here. It is x, right? So this is the argument here, variable here. So now you are evaluating this for each y. For example, if you pick y1, it is y1 x y1. Y2, it will be y2 x y2. So these are now constants for a fixed y, right? Then that is linear function in x. Okay. So that means this guy is convex because it is just supremum of linear functions. Okay, fine. Evaluated at different y's. Okay. So this is a beauty here. So we had a very complicated function which we cannot even visualize. It's very difficult. Now using this trick, within second, we can say that this is convex. Okay, this is a supremum of linear functions. So I can say that this is convex. Okay. So these are some, this kind of, this is the use of learning this course. So this kind of expressions often come across in your daily research. So then you should be familiarized with this basic stuff. So the course is arranged or the textbook is arranged by picking several such examples from many fields, not only from our field, many fields.
But how can you say y is constant?
I'm not saying y is constant. What is this guy is doing? So pick all y's which is having unit norm. Okay. So then, so what you are doing is, for example, you pick y1, where y1 norm of y1 equal to unity. Okay. And keep this. Okay. Then pick y2, keep this. Like that, you pick all the y. Okay. So you have different y's, infinite y's. Okay. And now for each y, it's constant, right? Now what you are doing is take the maximum, or here take the supremum of those guys. So now in fact, what we are doing is the supremum of linear functions. Okay. So for a specific y that you pick, this is constant. Y is constant, right? Yeah, that's what I mean. Yeah. So that is pointwise supremum.
I have to go.
Now I think we can make a pause here, short break.
I'm understanding.
Yeah. Okay. So let's continue. So we saw what is pointwise supremum. Also, one point we saw that a need not be convex here, right? So what is a here
Wait,
in this problem? So here we have in this general framework we have y belongs to a, right? So what is the set here? Set a here. Let me just check whether this is recording. Yeah, it's recording. Yes, here a is like a unit norm circle, right? By two. So it's something like, for example, if you take a, yeah, this is two norm, sorry. So Euclidean unit norm. So it's like a circle. It's a circle. Okay.
Okay.
So is this a convex set?
Yeah.
It is just a circle. It's not less than or equal to 1. It is equal to 1, right? Here, this guy. So this is just this boundary. So this is not a convex set. Okay. So only because we saw that we state that this property to exist, a need not be convex, then only we can go for this. Okay. Later we will see that in pointwise when we take a infimum or when we go for minimization problem, this is not the case. There a has to be convex. Okay. Yeah. So let's yes.
It's like there is no interior constant.
Yeah, this is not convex because if you pick any 2 points, this line is not included in the set here. Composition with the scalar function. This is a very useful thing. Let's see what it is saying. So we have a function defined like this. F of x is h of g of x. This is called composition. So h, the inside function g maps from Rn to Rn. So you have x in Rn, and now you are considering a function g of x which maps that to a real value R. Again, you are taking passing that to the argument of another function h. Okay, so that is from R to R because here we have R, right? From there you are again mapping to a real number using this function. So now we are checking whether f is convex or not. So under certain conditions of h and g, this will be convex. Now we are seeing what are those conditions. So let's directly start from the proof, then it will be easy. So so this is a simple example where I consider n equal to 1 because then we can directly use the different derivative. Otherwise we have to go for gradient. Okay, but still this proof can be extended to any n. So this is not the complete proof, just for a special case n equal to 1. But this proof will be very useful in remembering these rules. Okay, that we'll see, don't worry. Yeah, so we have f of x defined as h of g of x, right? So what I do is here I like I take the second order condition to check this. So first I differentiate f of x, f dash x, okay, which is this one, right? So first you take, this is the chain rule, right? h dash g of x into g dash x, okay. Again, second derivative, again you apply chain rule, right? So first keep the one thing constant and find the derivative of other. So then you again will get a g dash x that will form this square here. Then the second term here, okay. So this is simple chain rule. And now we will observe what under what condition this f is convex. So we know that f is convex when the second derivative is greater than or equal to 0. Okay, so now we will check. So for my f to be convex, this guy has to be positive or non-negative, right? Greater than or equal to 0. So here we can say that. So now we are going to check when is this guy non-negative. So this is a positive quantity. It's a square, right? So that will always be greater than or equal to 0. Now, so now we are focusing on this term. And so what is this guy? H dash gx, H double dash gx. This will be positive. So what my point is, for this expression to be positive, both the term has to be positive, right? So now we are at this term, first term. So this is already positive. For this to be positive, that means H double dash is positive. So like sometimes I say positive, that means non-negative. Okay, so it's difficult to say non-negative each time. So unknowingly sometimes I say positive, but you should be understand that that is greater than or equal to 0. Yeah, so this is non-negative, means what? H is convex, right? When second derivative is non-negative, that function is convex. Okay, so now we saw that first term is positive when H is convex. Second term, we have two quantity here. Now this can be positive under two conditions. One is both these guys are positive, or second one is both these guys are negative, right?
Yeah.
In this condition. So these are these two conditions. So this is positive, this is negative. Okay. Yeah, so what happens when so now we are saying that both these two guys are positive. So G double dash is positive, that means G is convex, right? H dash is positive. So when you say that a first derivative positive, what conclusion you can make about that function? It is non-decreasing. A function is non-decreasing, or like the function has a shape like this, okay, increasing, then that its derivative will be positive. Okay, this I think we already saw in the last class. So here this is non-decreasing, right? I will use this notation for non-decreasing. And okay, so that is one condition. Okay, so either this can be both positive, or now we can come to the negative case. So this can both be negative. In that case, what happens? G double dash is negative. Okay, negative or 0. That means G is concave. H dash is negative. That is H is non-increasing function. Okay, so now we have our rule. So what is the rule? For my function f to be convex, first of all, H has to be convex. So this guy has to be convex. There is no doubt in that. And G, then this condition must satisfy. Then there can be two conditions, either this guy or this guy. Okay, so for H is convex, G is convex, H is non-decreasing, then the function is convex. Or the second option is H is convex, G is concave, H is non-increasing. Okay, so that's what it's written here. F is convex. Okay, so you don't need to remember this. It's maybe difficult to remember. Maybe you can remember one case. F is convex when, of course, H has to be convex, and G is convex, and this guy is increasing function, non-decreasing. That means increasing. So it's like everything is positive, right? When we say convex, we have an impression of a good feeling, right? A positive. So this is convex, positive, increasing. That means the function is convex. Maybe you can remember that one, or don't worry, just derive this. This is very easy, and then check it. So other thing is, here we were making statement about convexity, if f is convex. So similar conclusion, similar statement we can make for concave function also. So then we are not explaining that here, but I'm just saying that you just reverse the sign and do the same operations here. Okay, so then you can again come up with two more statement for concave function. Yeah, so that's it. Now we'll see some example. Exponential g of x is convex if g is convex. Why? Here what is our h? We have a form like h of g of x. So here what is s? H is exponential, right? And g is just g here, right? So it is given that g is convex. So this is given, okay? And what about exponential function? It is we already saw in the first class that it's a convex function, and it is increasing or decreasing. It's a increasing function, okay? So what is this condition for me? H is convex, increasing, and g is convex. That means together this function will be convex. And another function is 1 by g of x. Okay, so here what is h? H is like 1 by y. Okay, h of when you take h of g of x, it is 1 by g of x, right? So that means h is like you just take the reciprocal of the argument. Okay. Now here it's given that g is conjugate, so this is given, and g is positive. That's what it's given. So g is positive means two things. One is uh, that means, so this is the graph for 1 by x. Okay, so now you are saying that g is positive. That means you are just considering this positive part. Okay, in that part h is decreasing. Okay, so what my point is, 1 by x can be increasing or decreasing depending on whether it's a positive. Okay, here also it's decreasing, right? Yeah. Yeah, it is decreasing always, but just here we are considering the positive part. So in that positive part also it is we can say that is decreasing. But the other important thing is why we are saying positive is whether this is convex, h is convex or not. If you consider both the domain, both positive and negative part, then you cannot say that this is convex or not. But if you can consider the positive part only, r plus or r plus plus, then you can say that this function is convex. This we already saw in the first class or in the last class. Like this function 1 by x will be convex only when we can consider the positive part r plus plus. Yeah, so then now we have the conclusion. So g is concave, h is convex, and h is decreasing. That means this is convex. I think this is the second condition. Okay, so like that you can check different things. Now, yeah, we saw this. Now vector composition. So here we were talking about a scalar thing, h is from r to r. Now we will extend the same thing, but now my function g maps from, so my x is in Rn, g maps from Rn to Rk, okay, then h is from Rk to R, okay. So now this is involving the vector. So this is my function. How my function is defined? F of x will be h of g of x. That means h of several vectors. How are you forming that vector? These are the components g1x, g2x, g3x. Because g1x is mapping to Rk, that means you have k components. These are the components. Okay. And so now we will again do the same thing. Okay. Only difference is instead of derivative, we have a gradient here. Okay. This is involving vector differentiation. Okay. So you can, as I said, I mentioned a book in the last class, matrix cookbook. It's not a book. It's like a document, well-documented document. And you can check that how to differentiate, and I think it's there, or you can also see the appendix of Boyd's textbook about gradient and Hessian, and you can derive this easily. And so it is something similar to this, but only difference is instead of derivative, now we have gradient, and double derivative we have Hessian. Yeah. So now how do you like, now we can come up with a similar rule. Okay. Just as for this function have to be convex, just make that assume that this is guy is positive greater than or equal to 0, and see what happens to each step. So let's take an example. Yeah, first guy is this log gix. Now just see what is that. So now if you consider the original composition, now my h is like a log, okay, and g, we have g, right, g and h here. Now what is this doing? H is log,
Yeah, so
h is concave,
yes, because
H
minus
is,
log of is like convex, right?
yes, so
log
log
will
is
be
concave, and h is increasing, log is an increasing function, or yeah,
Yeah, yes, yes,
and g is concave.
yes,
It is given.
yeah.
Why it's given? It's to be positive, g to be positive, because we are taking logarithm of that, right? So if g is 0 or negative, then this doesn't exist, right? It's not defined, so that's why it's given positive. So then what can we say here is that, so g, okay, h is concave, right? So then what will be this guy? So this is case one. For first case, this guy will be, can you say h is concave?
Mm.
So what is
So
this?
overall is concave.
No,
No?
how can you say that? I'm asking, so now we are checking the sign of this quantity, whether this is positive or not.
Okay.
So I'm just asking whether these individual terms are positive or not. How? H is concave.
Then
So the H is concave, that means this will be, uh, this matrix will be negative, not positive semi-definite, okay? This will be negative, okay? That means when you say a matrix is negative, then X transpose AX will be less than or equal to 0 when A is negative, okay? That's the definition. So that means this will be negative. Yes. H is concave. Now you take differentiate twice, okay? You have gradient del square, right? That will be negative, a negative matrix.
So the basic definition of convexity is second order derivative should be less than or equal to 0. Second order gradient is of a function less than or equal to 0, which is
no, greater than or equal to 0. That should be positive.
Positive, yeah, this is what I was confused. Both the terms should be positive, right? For it to be convex.
Yes, it should be, if that to be convex, both the terms should be positive. But we are checking whether it's convex or not, so it can be concave also.
I'm just having a pre-assumption that it is.
No. So we are just seeing what it is.
Okay.
So this is negative, okay? And what is this guy, delta H? This is an increasing function, H. So the derivative, you can just roughly
So it's like
speak as,
negative or negative.
no, if a function is increasing, then its derivative will be positive, okay, or non-negative, okay. Okay, so this is, I made a wrong statement. If a function is non-decreasing, then the derivative will be non-negative, okay. So that's a correct statement. But sometimes when we say that okay, function is increasing, then derivative is positive, okay, that's also correct. Yeah, but yeah, when you write, you have to make the statement is actually correct, okay. Yeah, so here we have h is an increasing function. That was our statement. So this guy will be positive, okay. And what about this guy? G is concave function. So this guy will be negative. So overall, this will be negative. Positive into negative, right? This will be negative. So overall, this quantity will be negative. So that means F is concave, not a concave. Now we can come to the second case. So where, okay, one thing is here, one thing that I forgot to mention is here, we are considering this G, H, and conditions of G and H, and saying non-decreasing, but it has to satisfy in each argument. That means That means, for example, if you take here, you have a quantity like delta H, gradient of H transpose something like G double dash, right? Both are vector. Okay. So this is like a inner product between two vector. This is an inner product between two vector, which will be having delta H1 into G1 plus delta H2 into G2, something like that. It will be having terms like this. So in the case of real a scalar composition, it was easy. But here to say that this is positive, we can only do that. Only way that we can say this positive is like saying that it's positive in each of these arguments. Okay. So whatever the statement that we made here was in each argument. That means in each component that should be satisfied. Okay. Yeah, then only we can say that the overall inner product is positive or not, right? Otherwise it can happen that these two guys are positive and this guy is a large negative and the overall can go to negative, right? So that's why we are ensuring that this should satisfy in each argument. Yeah, so now we come to the next one. Yes, so what is this function, this is log sum exponential, right? Log sum exponential here, log sum exponential of g of x. So we already saw in the last class that this function log sum exponential is convex. This you can refer to the last class. So now I have a convex function, and now g is convex. Now you can simply check this. So for the case 2, this guy is positive. Why? Because there is a different color. Not G. Here it's about H. H is convex. So this Hessian will be positive definite. So this is positive. Plus, what happens to the first guy here? H. So log sum exponential is an increasing function because you are taking log sum and exponential. But everything is increasing. So this will be non-negative. Okay. And G, yes.
We are saying that log functions are countable. One is log functions are countable. So
No. This is different. This is not log function. This is log sum exponential.
log of x can be written as sum of some x.
Yeah, but then you are like then you have to see what is that's again a composition, right? Log sum exponential. So just by seeing outside a log, you cannot make a conclusion. Okay. I think we proved this.
In this case, we have to check like this.
Yeah.
Log exponential x1 log exponential x2 plus like that.
Yeah, you can just I don't repeat that. You can just see the previous slides. Okay. Yeah. So so that's why we are studying this, right? Composition. So the moment you see this, you cannot make a conclusion just from the x function, the outside function. Okay, it can be anything based on the inner functions. Yeah. So okay. So we will. Yeah. So what is this guy? Here g double dash x, that is like g is convex, so this guy will be negative, right? So overall this is no what
G
happened?
is convex, so it will be convex.
Yeah, sorry. Okay, yeah, I made a mistake. G is convex, so this has to be positive. So overall this will be positive. So that means this guy over here log some this guy is this guy is convex. So here see you have a log outside and it's a convex function. That's vector conversion.
Suppose this kind of question is there in assignment, so we do not have to give like a whole scenario, right? We can say like how we have explained it. Okay, this is increasing, so this is convex, and
yeah, you can
like that
you can say and also maybe you can just put this guy and so come back to this equation. I have these terms which are positive, negative, then my conclusion is this. That's the statement. Yeah. So now yeah. So now the thing is, another important thing is, so many statement that we made before can be visualized under this composition. For example, we saw that this is, we said that norm of affine function is convex, right? So this is again something similar. Here my h is no, okay, and g is g function g is like an affine function, right? So what is this h? H is convex. H is convex, and norm is an increasing function, okay, and g is convex. So this is convex, increasing, convex. That means overall will be convex. This will be convex, okay. And or in general, I consider a function f of ax plus b. Okay, I just say that f is convex, and yeah. So here what is my h? H is this f, right? I will use the same notation what we follow instead of f. So here what is my h? H is f, and g is this ax plus b, this guy, right? Right. So here I just say that f is, what we saw that is a linear function of a convex function is convex, right? We didn't say whether f is increasing or decreasing. That's my point. So we just saw that, we just say that here in this case h is convex, and here we already know that since this is an affine function, g is convex, but still we stated that this guy is convex. Why? Because here I didn't make any assumption. So I'm talking about the previous slide. Yeah, this guy. I'm talking about this guy. So I just said that here f is our h, right? F is convex. Okay, I didn't say whether it's an increasing or decreasing function. But still we said that the overall composition is convex. Why? Because here, this, since it is involving affine function, when you take second derivative, f double dash ax plus b, it will be something like, so what will happen, it will not have this second term. Okay, it will be something like the second derivative will be something of the form, I guess you can just see, it will be something like this. Okay, so that means, see why we are having a second time here, because when we take the first derivative we had g dash x here, right? But now here, since what is g dash x, g is my ax plus b, when you take g dash it will be just a constant, right? So now that will be a constant here. So now here in the second derivative, this term will not be here. Okay, we will only have one term. So again you are taking the derivative, so just one term. So that's why we have this increasing and decreasing. We don't have increasing and decreasing part here. We just then you can just differentiate this function twice, and just evaluate whether that is positive or not. So that means for this function to be convex, just f need to be,
Increasing term will not come because in the second
yeah.
derivative it
So
will become 0.
irrespective of whether f is increasing or decreasing, that is convex. This is happening only because this guy has a special structure of affine function. This guy is a our g is an affine function. Okay, yeah. So I'm just mentioning, you can just verify this. And yeah, so now we move to the next topic. So we saw what is maximization or supremum, right? Now we move to infimum. So now infimum also preserve convexity, but not in general under certain condition. So what is the condition? First, f of xy has to be in convex in both x and y. Okay, jointly in x and y. That means if you fix y, it has to be convex in x, and if you fix pick a particular x, it has to be convex in y. That's what this means. Jointly convex in x and y, and C has to be a convex set. So remember here, while we considering supremum, we didn't put any constraint on C, but now for this to satisfy G to be convex, C has to be convex. So that's a very important thing. So why? Because it is coming from the proof. Okay, so let's see what is a proof. So I'm considering a value epsilon without any assumption, just one assumption, it's positive. Okay, and then there are, I can find two values y1 and y2 from the set C such that f of x function evaluated at those points is less than g plus epsilon. What is g? G is the infimum, right? So like if you remember, you have a set S, and infimum will be, let's consider this as the set. Okay, so infimum will be this point, right? Okay, so now what I'm saying is I can pick a point y here, okay, such that mm, so here maybe I'm mm, explaining you with respect to a set. Okay, anyway, such that if I add a small an epsilon, a positive quantity to the infimum, it will fall within the original set function. Okay, that means so infimum is like the lower bound, right? So what I'm doing is I am adding a small positive quantity or a large. I am not putting any restriction. I am adding a positive quantity to that lower bound. Then that will be that will be above of some of the elements in the function. So then what I'm saying is I can pick y1 and y2, some y1 and y2, such that this can happen. Okay, so with some epsilon, some positive epsilon. Now let's take this quantity g of, now we are seeing whether g is convex or not. G of this convex combination between 2 points, which is how g is defined. It is infima of f theta x1 and y, right? The same definition. Okay, now what I do is I just see. Okay, so now I remove this infimum. Okay, infimum is like a minimum value, right? So I remove this infimum, and I can now say that it put this inequality here, right? It's greater than zero. Also what I do is there is a y, since it is a convex set. Okay, I replace y with a convex combination of this y1 and y2. So if it's a convex set, any point I can use visualize as a convex combination of some two other points, right? So I do that. So from here to here, I just remove the infima and replace y with the two other quantity. Okay, so that means here this inequality will fall. Now this is, we assume that this is jointly convex. So now I am applying the inequality of convexity. Okay, now here, since we said that I can pick y1 and y2 such that this inequality holds, right? I add an epsilon to the infimum value, then I can make this inequality. So that I applied that here and make this statement. Okay, now what I'm saying is that it is like this inequality holds for any epsilon, any positive epsilon, right? We didn't make an assumption on epsilon. That means it's like it is slightly confusing, but you can later read and understand. But I am giving you a hint. That means you are saying that A is less than or equal to B plus epsilon for any epsilon. What does that mean? That means A is less than or equal to B, right? I'm saying that there is no condition on it. For example, if you say 2, 3 is less than or equal to 2 plus epsilon. If you say this, then it is not valid for any epsilon, right? Right here I'm saying that this is valid for any epsilon. That can happen only when a equal to b. So then okay, then this can be I can drop this and write this inequality and the function to be show that the function is convex. Yeah, so
it's like b is already greater than or equal to
yeah,
A, right?
yeah. So
And we are saying like epsilon is a positive
yes,
value.
positive.
So if you add that, then obviously
Yes.
it will.
Okay. So for any epsilon, okay. Yeah. So the important point here is you can read this proof, and maybe some parties you may need time to understand, but I hope you know the overall flow of the proof. But the important part is that we use here the concept that y is c is a convex set. Then only we can write this. Okay. So that's why we are saying that this is not valid for any set C. C has to be convex. For infimum to preserve convexity, C has to be convex. Some example. First example is a quadratic function of this form. Okay, so this is like I can write this expression as x y transpose a b transpose c into xy. These are vectors actually. So this is what this guy is. Okay, I can write this like. So now, yeah. So this is convex under what condition? This has to be positive definite, right? This we already saw. And then again, one more assumption: C has to be positive. We'll see why this C is positive. Now, so if you minimize this over Y, okay. So what we are doing is we are just checking this. So I'm minimizing this over Y. So if you minimize this function over Y, that is g of x equal to infimum y f of x y, you will get this solution x transpose a minus this one. Yeah. So here I am writing the proof for that. You can check it later. Okay. So this is not complicated. Just some steps. You can check it later. Okay. Yes. So then you can come up with this solution. Okay. That means but we already saw that this preserves convexity, right? So here we have in the proof we have a C inverse. So then this can happen, or in the solution we have this term C inverse. This can happen only if this is this should not be 0. Okay. Yeah. So the conclusion is we have a convex function since this matrix is positive semi-definite, and now we have a solution which is a function in x, and we know that infimum preserve convexity. So this is also the solution is also convex. That means this guy is positive. Again, this is a function, a quadratic function, where we have a matrix here that is positive semi-definite, because this is a solution after this infimum operation which preserve convexity. So this is a convex function, and hence this guy is a positive semi-definite guy. So this special matrix is called sure complement. Okay, so what we saw that in this case, sure complement is a positive semi-definite. Okay, so I just give you an information about sure complement from the textbook. You can read this later. Okay. Now another example is distance to a set. So we saw in the previous example maximum distance to a set. That is a convex function. Here distance to a set, that means when you say distance means distance between 2 points means it's a minimum distance, right? So distance to a set means that will be the minimum of this, maybe somewhere here in this case. Okay, so how do you find that? Pick all y's and find this distance. Okay, and take the infimum of that. Okay, so this is also convex function. Important thing is that this is convex only when C is convex, because that comes from the proof, right? Or here we saw that this has to be convex. But earlier when we were mentioning about maximization, I draw a set like this because C need not be convex in that case. But for minimization, this has to be convex. Yes, so we move to another. So we will stop with this slide. Okay. Perspective function. Yeah, so a function is perfect. What is a perspective function? We have a function f from Rn to R. Okay. Now we form a new function g, which is from Rn and having an extra argument. So it's like x and t. Okay. How do you define that? It's simple. You take f and consider x by t. So remember we were studying perspective, the same concept in under set, right? So you have x1, x2, something like x3. Then we divide this by x3 each time by x3, right? This we solve, right? So let's say this is t here. We have t here. Then we remember we divide this with t and talk something about. So this has some connection with that, but we don't go into detail. We do not go into detail since we don't have time. But I just state that my perspective function is something of the form t into f into x by t. This is a t. So what will be the domain of this function? It will be x by t such that it will be x comma t, sorry, x comma t such that x by t should belong to domain of f, right? Because we are putting this guy inside as an argument of f. So this guy has to belong to the domain of f. And the additional constraint t has to be positive. So this is how this function is defined. And now what we are saying that this is again if f is convex, G, G is also convex. Now it is in x and t. So G is convex in x and t. So some example. One is, let's take this function f of x equal to x transpose x. So we know that this is convex, right? And hence, another function x transpose x by t for t greater than 0 will also be convex. How do you get this? So just plug this formula. You have t here. Now x by t, right? Transpose x by t. Okay, so one t will get cancelled and we have this one. So what my point is, this function can be visualized as a perspective function. Okay, then we can say that if f is convex, this is convex. Another function is f is minus log x, which is a convex function that we know. So now what is the perspective of that? T into minus log x by t. Then you will get this guy here. Okay, and that is again convex, and this is called relative entropy. In maybe if you have studied information theory, this is you might be knowing this. Okay. Anyway,
P log T is it convex? The second term.
No, I'm just saying about the end of term. T log t minus t log x is convex in. This is not simple. In both t and x, generally convex in both t and x. Okay. Okay. Why? Because from this rule, we didn't say the proof. We didn't see the proof, but this is this function for so convexity.
Because if G has to be convex and both the terms should be convex.
But how do you say that this is t is not constant here? This t is an argument here. No, what I'm saying is this is not like minus log x. It's t into minus log x. So this is not convex. I'm not saying this is convex in just x. It's we are observing the convexity in x and t. Okay. Yeah. So last thing, a similar guy. F is convex. Again, we saw a function like this while we are studying set. So f is convex. So instead of t, So it is something of the similar form, but now we have C transpose X plus D and affine time, and then F of an affine time divided by this affine time. This guy also will be convex. Yeah, of course. So then this has to be, you are taking this inside the argument of F, then that should belongs to domain of F, and this guy is positive from the definition of this special category of function. Okay, I think we will stop here.